So today we shall be studying about second order partial derivatives. So in the last class we have seen what are partial derivatives. So we have also studied these first order partial derivatives. Suppose you have some function f corresponding to these three variables. That means this function f is dependent on x as well as y as well as on z. Suppose this is the case. Then the first derivative of this function f with respect to x, that is defined by calculating the derivative of this function keeping all other variables, that is y and z, as constants. And similarly, when you calculate the partial derivative with respect to y of the function f, then you will keep x and z as constants, and in the next case when you calculate the partial derivative of f with respect to z, so you will keep both x and y as constants. So this is what we have already done. So now let us see how do we define the partial derivatives of second order for a particular function. So they are defined like this. Notation here is we can either use f and double x in the subscript of this function f. This is notation. Another notation is this one. That means you could write del square f divided by del x square. So remember this notation, this del, this operator, this is the notation, and it is either pronounced as del or sometimes it is also known as curl. So we'll prefer this term del. So del 2f divided by del x2. So that is the second derivative of the function with respect to x. And by definition, what would be this? This would be, you could write this as the partial derivative with respect to x of the function del f by del x. So basically what you are doing, you are taking the derivative of this first derivative. So that is what we are doing. We are taking the derivative of f of x here. So that means, and we are taking it with respect to x. So that means we are only changing x. When you change x, here you have x plus h and here you have x. The y term, that will remain constant here because we are taking the partial derivative with respect to x only. So that is the definition for this first derivative with the second derivative with respect to x. And then what would be the double derivative with respect to y of this function f? So it is denoted by this expression or this notation, right? So here what we are doing, we are taking the partial derivative with respect to y of this function del f upon del y. So we are taking the derivative of f of y and we are taking it with respect to y. So that means here x would be constant, it will be same, whereas we'll make change in y plus k term. So it is y plus k and y. And next we have mixed derivatives. That means firstly you will take the derivative with respect to x. So that is, we have this term del f upon del x, and then you will perform the derivative with respect to y. So it is y here. So this whole term is represented like this. So firstly we have to take the derivative with respect to x. So accordingly here it would be fx and here it would be fx. And because now we are taking the derivative with respect to y partially, so we will keep x as such and we'll take the derivative and we'll change the coordinate y accordingly, where this small k represents the distance between y, these 2 points, this point and this point, that is y plus k and y. And then you have this derivative f of yx. That means firstly you are taking the derivative with respect to y and then you are performing the derivative with respect to x. So order here matters according to the subscripts. So firstly with respect to y and then with respect to x. So this is the notation, and here because we are taking the derivative of this f del f by del y, so that means this is f of y and here also f of y, and because we are taking the second derivative with respect to x, so the change is seen only in this x coordinate and y coordinate is kept as such. So this is the basic definition and some of the notations how you could define these second order partial derivatives. So now let us see one example. So now this question is given to us that find all the second order partial derivative of this particular function. So the function is given to be x square y plus cos of y plus y sine x. So now what are all the partial derivatives? First is this fxx, then is fyy, and then we have fxy, and then we have fyx. So we'll compute all four of these. So firstly we'll require the first derivatives with respect to x and with respect to y. So how do you obtain these quantities? So what you do, you just differentiate this particular function firstly with respect to x. So that means when you differentiate this with respect to x, keeping y as constant, so here y would be constant. So because y is constant, the derivative of this term is 2x and y as such. And because y is constant, so its derivative is 0. And because y is constant, so y would come as such here, and you will take the derivative of this sine x. Its derivative is cos x. So that is how you obtain f of x. Next we will compute this f of y, the first derivative with respect to y. So here we will keep x as constant. So when you keep x as constant, your function f of y would be equal to this quantity. See how? Here your x square is constant, so it will come as such, and the derivative of y would be equal to 1. So 1 into x square. Then next term is cos y, and we are taking the derivative with respect to y. So derivative of cos y is minus sine y. And then here y into sine x, because x is constant, so sine x would be constant. So this term would come as such, and then we'll perform the derivative of this term y, and the derivative of the term y would be nothing but 1. So finally we reach at calculating the first and the first partial derivative with respect to x and with respect to y. Now the next task here is, using this fx, we can compute fxx and we can compute fxy. So what we will do, we will first differentiate this partially with respect to x. So now because this is also a function of x and y, so what we are doing, here 2y, that would be constant, so they'll come as such, and then what is the derivative of x? That is equal to 1. So this is the term, and then because y is constant, so this term would come as such, and then what is the derivative of cos x? It is minus sine x. So this is how you obtain this quantity, and then you will partially differentiate this f of x with respect to y. So f of x with respect to y, so what will you get? You will have fxy, which is also a function of x and y, right? So here you will keep, because we are taking derivative with respect to y, so here you will keep x as constant. So if when you keep x as constant, so this 2y would come as such, 2x would come as such, right? Yes. So we would have this quantity, and we will perform the derivative with respect to y. So that is equal to 1. And then because x is constant, so cos x is constant, it will come as such, and then the derivative of y again is equal to 1. So this is our fxy. Similarly, we can compute fyy and fyx, because now we have this fy, so we can firstly differentiate this with respect to x. So correspondingly we will keep y as constant for doing so. When y is constant, this first term's derivative would be 0. Here we have minus sine y, its derivative is minus cos y, and we have sine x, this is also independent of x, it is also independent of y, right? So I'm sorry, we are calculating f of yx, right? So when you compute yx, so that means you are taking the partial derivative with respect to x. So we will keep y as constant. When you keep y as constant, your first term would be x square. So its derivative would be 2x. And then because this term is independent of x, so the derivative of constant term, and y is constant, so sin y is also constant, so its derivative is equal to 0. And the derivative of sin x would be cos x. So this is this quantity f of yx, and when you compute the partial derivative of this particular quantity with respect to y, so what we will do, you will keep your x as constant. So when x is constant in the first term, because we only have constant, so its derivative would be 0. So we have 0 here, and then the derivative of minus sin y would be minus cos y, and then the derivative of sin x, because x is constant, so this would be equal to 0. So now notice here that the quantity, these two quantities, f of xy and f of yx, they are equal here. But this in general is not true. That means we cannot every time conclude that whatever is this quantity f of xy, that is equal to the quantity f of yx. They will be equal. We have this result that stating that these two derivatives, second order derivative, they would be equal whenever all the partial derivatives like f of x, f of y, fxy and fyx, they are defined, first thing, and are continuous throughout the region. If that is true, all the partial derivatives are defined and continuous, then these two partial derivatives are equal. So that is the result. So next we will discuss certain examples. The first question is, given z multiplied by x plus y, that is equal to x square plus y square. This is given to you. Then they are asking, show that this quantity is equal to this quantity. So here notice that what we are required to calculate del z by del x and del z by del y. Here also on the right hand side, we only require these two terms. So firstly we will compute what is the partial derivative of z with respect to x, and then the partial derivative of z with respect to y. So here note that z is depending upon firstly on x and then upon y. So this is the case here. So firstly we will write the explicit form of this z. So that means we will shift this term on the right hand side. So that means now you could write z as some function of x and y. So once you obtain this kind of term, like equation number 1, now we are ready to perform the partial derivatives with respect to x as well as with respect to y. So now when you differentiate this quantity partially with respect to x, you have to perform on the right hand side the quotient rule. So for that we will suppose this is u and this is v. So we would have the v square in the denominator, and in the numerator we would have v as such the derivative of u minus u as such the derivative of v. So what is v? V is x plus y, that is as such, and then the derivative of u, that is the derivative of x square plus y square, and partially with respect to x. So that means it is equal to 2x, because we are now keeping y as constant, and then minus as such u, that is x square plus y square as such, the derivative of x plus y partially with respect to x. So it is equal to 1. So this is the quantity that you have. Now you could simplify this and solve this a bit. So this is the value that you got from here. And next what we'll do, we'll perform the partial derivative of this particular term z with respect to y. So here we will keep x as constant. So again we will apply this quotient rule over here. So denominator square, denominator as such, the derivative of numerator. Now numerator's derivative we are taking partially with respect to y, keeping x as constant, so it would be equal to 2y, and then minus numerator as such, x square plus y square, and then the derivative of denominator, that is equal to 1. So you could simplify this term, and this is what you got from here. So now once you have this del z by del x and del z by del y, so we have to show this quantity. So for that we first consider this left hand side, that is del z by del x minus del z by del y whole square. We have this quantity del z by del x and the quantity del y by del z, del z by del y, sorry. So we can substitute it here. So it would be, when you substitute this quantity here and this here, so you finally have this quantity. So now because the denominators are same, you could club the terms. So this term cancels with this one, and when you simplify this, you will have this as 2 times of x square minus y square whole square. So now because this is x square minus y square, so you could open up this term x minus y, x plus y. So 1 power cancels with this 1 power, right? So you are left only with this term. Now for the right hand side, because right hand side this term was there, so we just substituted the value of del z upon del x and del z upon del y, and then we have simplified the terms. So here you could take the LCM and solve this a little bit, some of the terms get cancelled out, and finally you see we are left with x square plus y square minus 2xy. What is this quantity? This becomes the square of x minus y whole square. So you could write this to be this term. Now you see this right hand side is exactly equal to the one that you got here for left hand side. So that means we have shown what we are required to show, that the left hand side is equal to right hand side over here. So let us now solve the second question. It says that u is given to be log of square root of x square plus y square plus z square. We have to show this quantity. So now notice here that we require the second derivative with respect to x, with respect to y, and with respect to z of the term u. U here is a function of x, is a function of y, is a function of z. So firstly we'll compute what is del u by del x. So that means we are taking the partial derivative of x with respect to y. So here we will keep x and y and z as constants, because we are taking the derivative with respect to x. So what would be this? Firstly we'll perform the derivative of log. So it would be 1 divided by square root of x square plus y square plus z square, and then the derivative of this power, that is square root. So it would be 1 divided by 2 square root of x square plus y square plus z square, and then the quantity within this square root. So its derivative partially would be 2x plus 0 plus 0. Why? Because y and z, they are constants, and the derivative of x square would be 2x. So we could simplify this. This 2 get cancels with this 2. So you would be left with the quantity x divided by x square plus y square plus z square. Here we have square root, here we have square root. So when you multiply these two, you have the power as 1. And similarly we'll then calculate, because we require the second derivative of u with respect to x. So we'll calculate the second derivative by differentiating this again. So when you differentiate this, here you have to apply the product rule. This term is your u, this term is your v. So it would be x square plus y square plus z square raised to power 2, and then this term would come as such, and then the derivative of the upper term, numerator, that is equal to 1, minus numerator as such, and then the derivative of this denominator. So it would be 2x plus 0 plus 0. So we can simplify this. So x square plus y square plus z square minus 2x square divided by x square plus y square plus z square whole square. So it would be minus x square plus y square plus z square divided by x square plus y square plus z square whole square. So this is equation number 1. Say similarly we'll calculate the derivative of u with respect to y. What was u? U was log of square root of x square plus y square plus z square. So this term would be 1 divided by square root of x square plus y square plus z square, and then the derivative of this square root, so it would be 1 divided by 2 square root of x square plus y square plus z square, and then the derivative of this inner term. So it would be 0 plus 2y plus 0, because we are taking the partial derivative with respect to y. So this 2 and 2 cancels here. So we are left with y divided by square root of x square plus y square plus z square. So again we have to take its second derivative. So that would be equivalent to x square plus y square plus z square. Okay, so this square root won't be there. Why? Because here the power is 1 by 2 and here also the power is 1 by 2. So they'll combine and make the power as 1. So this square root won't appear here. Okay. So when you take its derivative, so we would have by the quotient rule the square of this quantity, and then the denominator that would come as such, then the derivative of numerator that is equal to 1, because we are taking partial derivative with respect to y and we only have y here, and then minus y and the derivative of this denominator, so that would be 0 plus 2y plus 0. So when you simplify this, you will have x square minus y square plus z square divided by x square plus y square plus z square whole square. So say this is your equation number 2, and again we'll calculate what is del 2u divided by, firstly we'll calculate what is the first derivative with respect to z of u. So that would be 1 divided by, because our u was log of square root of x square plus y square plus z square. So our del u by del z, that would be equal to 1 divided by square root of x square plus y square plus z square, and then we have 1 divided by 2 square root of x square plus y square plus z square, and then the derivative of this inner quantity, so that is 2z. So this 2 and 2 cancels. So your del u by del z, that is equal to z divided by x square plus y square plus z square. And therefore what would be the partial derivative of u with respect to z twice? So it would be equivalent to, again using the quotient rule for differentiation, so it would be the square of this quantity. The denominator would come as such, the derivative of numerator with respect to z, that is equal to 1, and then the numerator as such, the derivative of this denominator. So it would be 0 plus 0 plus 2z. So finally you would have del 2u divided by del z2, that is equal to x square plus y square minus z square divided by x square plus y square plus z square whole square. So this is the equation number 3. So now we have all this quantity and we have to show that this thing is equal to 1. So we'll consider this thing. So we'll take the left hand side. It is equal to x square plus y square plus z square multiplied by del 2u by del x2 plus del 2u by del y2 plus del 2u by del z2. So what is this quantity? This is what we are required. So we'll substitute the values of double derivative here. So first term would be as such, the value of del 2u by del x2, its value that is equal to this quantity over here. So that is minus, we have this as minus x square plus y square plus z square divided by x square plus y square plus z square whole square, and then the derivative of and then we have the derivative of u, second derivative of u with respect to y. So it is x square minus y square plus z square divided by x square plus y square plus z square whole square, and then the last quantity is x square plus y square minus z square divided by x square plus y square plus z square whole square. Why this is so? Because the quantity del 2u by del z2, that is equivalent to this quantity, okay, and the quantity del 2u by del y2, that is equal to this quantity over here. So we have just substituted the values here. So now the next step is to simplify all these terms. So this would be the 1 power of this term x square plus y square plus z square cancels with 1 power here of each of these terms. So we will be left with 1 divided by x square plus y square plus z square, and we are left with minus x square plus y square plus z square plus x square minus y square plus z square. This is according to second term, this is according to first term, and then according to third term we have x square plus y square minus z square. So now you see this x square cancels with this x square, this y squares cancels with this y square, and this z square cancels with this z square. So what we are left with? We are left with 1 divided by x square plus y square plus z square, and in the brackets we have these three quantities remaining. So that is x square plus y square plus z square. So now you see this also cancels with this one. So the final answer is 1, which was equal to this right hand side. So we got what we were required to prove. That means we wanted to prove this quantity equal to 1. So we have shown the same. So I have one question for you. Please note down this question so that you could try this.